ground, okay? Our third dimension, Z, is now the vertical axis, okay? So we have 3 dimensions here. So how do we draw points or coordinates? Well, if I had, for example, 3, 0, 0, well, that's telling me that I have to move 3 units on the x-axis and I don't have to move anywhere else. So I would have a vector rather, right, here on, right on my x-axis. If I had the coordinate, let's say 1, 2, 3, and I don't have a scale here, so we're just going to approximate it. So then I would move 1 unit on the x, and I would move 2 units on the y, which should be double, and then I would move 3 units on the z. And that's where my point would end up, and then that would be my position vector. Okay? So that's how we draw on a 3-coordinate grid. So what we notice here with 3 dimensions is that now we have planes. So what are planes? Well, I have an XY plane. I have an XY plane here. So what's an XY plane? Any vector that lies on this plane has a component of 0 for Z. So its Z component would be 0. Why? Because we're not moving up or down at all. We're moving so many units on the x-axis and so many units on the y-axis, but we're never moving on the z-axis. So something that lies on, something that lies on the z-plane, I don't know, could be 3, -2, 0. And that would lie on the on the xy plane. Then we have another plane. Where's my highlighter? Let's do it in a different color. So then I can also have what's called the XZ plane. And so that means that those vectors would lie inside this box. And so if you guys had to guess, which component would be 0 now?
Y.
Yeah, Y would be 0. Excellent. And it's important to note that that these planes go on forever and ever and ever, right? They're infinite, so they don't stop. They're infinite. They can go as far up and far down and left and right, correct? Like I'm showing it right now just in the positive X and Z. Okay. And then we have one more plane. Let's do the last one. And what do you guys think it's going to be? So we've done XY, we've done XZ. So now we need YZ plane.
YZ.
Yeah. And so that plane runs this way. And I know this is very hard to visualize in 2 dimensions, but if you can imagine, it's a plane that runs vertically like this. And so the X component would always be 0. Okay, so that's a little brief explanation on the 3 dimensions. Okay, so now we have 3 coordinates. So now my standard basis vector I is 1, 0, 0, and J is 0, 1, 0, and K is 0, 0, 1. Any vector in 3D space can be written as an ordered triple in component form, just like we did in 2-dimensional space, but now we have that 3rd component, C. Or we can write it in standard basis form using our standard basis vectors, I, J, and K. The basic principle can be extended to include all vectors in R3. So if we have A with components x1, y1, z1, and B with components x2, y2, z2 as 2 points, then the vector AB would be x2 minus x1. We just subtract the x's like we did before, subtract the y's, and then subtract the z's. That's all that's new now, is that we have this 3rd component, but everything is the same. So similarly, now we're looking for the magnitude of vector AB. So the magnitude of vector AB is still the Pythagorean theorem, guys, but now we just add the 3rd component there. So Z2 minus Z1 all squared. Note vector addition and vector and scalar multiplication, excuse me, in R3 is the exact same. So all the same rules apply. So that means if I have a component, let's say -2, 3, and 4, and I have to multiply this vector by 3, then all the components get multiplied by 3. All the vectors get multiplied, all the components, excuse me, get multiplied by 3. Okay, sorry guys, just give me 1 sec. Christian, what's up, hon? Okay, so let's get back to this. Okay. All right, so example 1. I have points A, B, and they form opposite diagonal corners of a rectangular prism. So we are going to draw this together. So guys, this is my X. This is my Y. Z is the vertical axis. Okay, and we're always going to draw our planes in this order. Okay, just like this. Just like we always draw X as the horizontal plane and Y as the vertical plane. So 105 means I have to move 1 unit on the X. Then I don't move anything on the Y, but I move 5 up. 1, 2, 3, 4, 5. And then to draw B, I'm not moving anything on the X. I'm moving 2 on the Y. And I'm not moving up or down. So there's B. Okay, so we know that this has to form opposite diagonals of a rectangular prism. So I want you guys to go ahead and sketch the rest of this prism, keeping in mind that it has to form a rectangular prism. So take a minute to go ahead and draw that. Okay, you should get that, something like that. So hopefully everyone was able to figure that out. It's a good little abstract thinking exercise to get you guys thinking in 3D space. And it says determine the components of AB, of vector AB. Okay, we want it both in component form and in standard basis form. So I want to find AB. Does anyone have any idea what I can do?
Subtract B from A.
That's it. It's as simple as that. I have the components of B. I have the components of A. It's as simple as just subtracting the two. And so now I have my vector AB in component form. Who can tell me what this would be in standard basis form? No one? No one's with me?
Negative I
Yep,
plus 2j
yep.
minus 5z. Z.
Careful, IJ and?
Sorry, k.
Yeah, it's okay. And this is your standard basis form. Short form there.
Miss,
Okay, standard basis. Yeah.
if we forget like one or two arrows, is that a half mark or?
Yeah.
Okay.
It depends. I'm never going to get a half mark every single time you missed it in a question, but yes, you will lose marks if you forget your arrows. So be very, very careful. It's just like you lost marks for not writing the limit, right? If you were supposed to show a limit.
Okay.
Okay, so now we want to find a unit vector in the same direction as AB. So that means I can use these components. I want to use these components. I need the exact same vector. I just don't want it to have the same length as this. I only want it to have a length of 1. So the first thing we need to do is find out, well, what is the magnitude of AB? What is the size of AB? And so now we know we take the components squared and we add them together. And so the magnitude of AB, of vector AB, is 30. And so if I want the unit vector, I want the length to be 1. So I have to divide by root 30. And yes, we distribute this. And no, we don't rationalize, ever. So you can leave this like this. So here I have my component form and my standard basis. Oh, sorry, my component form. I need to put it in standard basis. So who can tell me what the standard basis would be? Just take your components and add I.
2 over root 30j minus 5 over root 30k.
Yes, thank you, Nicholas. Okay, so there's your standard basis. And there's your component. Give me 1 sec, guys. All right, example 2. Are there any questions about this? Okay, example 2. Determine 2 vectors parallel to I plus j minus 2k. These are all vectors, guys. They're bolded with a length of 1. So we want to use the components of this vector because I need a vector parallel to this, but I don't want it to have this length. I want it to have a length of 1. So let's figure out what the length of this vector is. These are the components of this vector. And so now I can find the magnitude of it. And so the magnitude is just going to be the square root of 6. So that's the length of this vector, but I need a unit vector. So if I want a parallel unit vector, well, in order for it to be parallel, we know it has to have the exact same components. But now I'm going to take those components and I'm going to divide by 6. So there you go. That's in component form. But now they want a second one. I need another parallel vector with a length of 1. What do I do?
Times by -1.
Yeah, just have it going in a different direction. Beautiful. That's all you can do. You're going to take the opposite direction. So it's the exact same vector, it's just running the other way.
How would you find something like a translation of the unit vector? Or is that hard to do?
No, you wouldn't. Yeah, no. Whenever you're asked a question like this, you're always taking the positive and the negative. Because remember, when you're talking component form, it's always a position vector, right? Component form is always giving you a position vector. It's never giving us a displacement vector.
Okay, okay, thanks.
Yeah, no problem. Okay, so FYI. So you see, if we were in school in person, you would see me probably using this. And so what you do is with your right hand, you have your thumb up, you have your middle finger acting as your y-axis, and you have your index finger acting as your x-axis, and sort of to give you an idea of what this plane looks like. And what should be happening is the x and the y-axis should meet at 90, and your x and your z and your y and your z are also meeting at 90. Okay, so if you can imagine, if you had a piece of paper flat on your desk, that would represent your XY plane. And then you get a pen and put it at the corner of the piece of paper and put it upwards, and that would represent your Z axis. Okay, so hopefully you guys can picture that. Here we're showing just how you have a vector starting at the origin here, and it has 3 components, A, B, C. Here I have A0, 0 because it's lying right on the x-axis. B would be A, comma B0 because it's lying right on the y-axis. Or excuse me, A, we're moving A units and B units, so it's just not moving up or down, so it would be lying on the XY plane. Okay, so we're seeing here a rectangular prism. Okay, so here we go. Here are the planes. So here's an example of your XY plane. So all the vectors in the XY plane, they can go in all different directions. They don't have to be parallel, right? All different crazy vectors on this plane. All of these vectors that lie flat on this plane would have a z coordinate of 0. And then here I have the YZ plane. And so again, you have all vectors in all different directions on this plane. And what would be common there? All the X coordinates would be 0. And on the XZ plane, all the Y coordinates would be 0. Okay? Cool. And this is your homework, guys, and your review. Be careful, there are errors in solutions for 11A and 11B. If you guys have any questions, I am here until 3 o'clock, of course.
When you talk about the components are equal, it doesn't mean same slope, right? It means exactly the same X and Y value.
It also means the same slope, though. Which
No,
one?
I'm
Tell
saying
me.
like, because couldn't 2 vectors have the same slope, but one be longer than the other?
Yes, they can. And one is a scalar multiple, but they're still parallel.
But that doesn't mean they're the same components though, right?
No,
Okay.
they would be different because they would be a multiple. So for example, so see this question, when I say this is the only way we can do it, it's because we're looking for a unit vector. If I wasn't asking for a unit vector, oh my goodness, there's so many vectors I can find. I just have to find different multiples, right? There's an infinite number of solutions. But because here I'm asking for unit vectors, this is why we only have these two possibilities.
Okay, thanks.
Does that make sense?
Yeah, makes sense. Thanks.
Yeah, good, no problem.